This is part 2 of estimating a population proportion using a confidence interval. We're going to start with a question that students often have, and that's the idea of confidence. So, in our everyday life, we know what the word confidence means when you're confident in something, confident in someone, but statistically, it does have its own meaning, a more mathematical meaning, let's say. Okay, so what we're going to do is we're going to use the diagram that you see here in order to better understand what the word confidence means. What you currently see here is basically at the bottom here is a number line. Okay, on that number line, we have our unknown population proportion. Now, I know that sounds weird. You're saying, how do we put an unknown number on a number line? Well, all of this is basically more theoretical than anything. We're just saying that let's assume that our unknown proportion for our population is right there in the number line. And you'll see above it, there's a dashed line that signifies its value all the way up throughout the different intervals that you see on the graph. So, yes, all of these lines here are just intervals. They're spans of values that have been calculated from a sample, let's say. Let's just give this some quick context. Let's go back to the problem back here where it said in a random sample of 250 employed people, 61 said they bring work home with them at least occasionally. So remember, we did all the work for this, and we eventually settled down on an interval of 0.199 to 0.289 for the proportion who bring work home. So remember, this is one interval computed from one sample. So let's just assume, for argument's sake, that that is this interval right here. So basically, I'm not going to be very specific, but let's say the values, what were they again? Hold on, 0.199, 0.289. Okay, so let's say like this right here is 0.109, this over here is 0.289, right? So this is the interval that we have calculated, and we put it on the graph. Now, according to this picture specifically, our true proportion P falls inside this interval. Remember, the whole point of using a sample in order to generate a confidence interval is to catch or contain the true proportion P. We want it to be in there, and it turns out that it is in this specific sample. Now, erasing this. So let's just say we didn't do this, but let's just say we go to another sample. Now, we all know that if we take another sample, we're likely to get a different p hat. And therefore, the interval is going to move. It's either going to move lower than in its span or higher than in its span. In this case, for our second sample, it looks like it has moved lower in value in terms of its full span than our initial one. But you'll notice that it does again catch or contain our population proportion P. We're going to keep on doing that. And in total, we are going to take 10 samples. Each one of the line is going to represent a confidence interval that represents a specific sample that we took. If we keep on going to our third one here, you're going to see that it's gone way lower than the other two in terms of value. In other words, lower on the number line. So this one is interesting, actually. This one does not catch P. So P is not in the interval. That opens up a whole nother can of worms here, because that implies that our interval could be wrong. And by the way, it could be. And that's why I'm explaining this to you, so you understand this fully. So let's just keep on going with the other ones. So we have sample 4, 5, 6, 7, 8, 9, 10. All of them are added to the diagram. We're just basically simulating in our brain. We didn't do any math. But let's just say this is what happens with the 10 samples. We create 10 confidence intervals for the true proportion, and we end up with these spans of numbers. Okay, so here's the punchline, right? If you recall in this problem, this was a 90% confidence interval. Well, If you look at our scenario here, in how many of the intervals out of the 10 did we actually contain p? Well, if you look at them and count them, in 9 out of the 10, we actually caught the true proportion p, and we contained it in the interval. This is the definition of 90% confidence. In other words, if you're asked to find a confidence interval at 90% confidence, the results will only yield the correct proportion p in your interval 90% of the time. This is very challenging for students because they're basically, in their heads, they're going, you're telling me that this interval is wrong 10% of the time. And that is true. Statistics is not a perfect science or perfect math, however you want to put it. It is an estimation. And when you estimate, you're not always going to be right. Okay, let's see if you're following here. Over on the right, it says, if a confidence interval for P, or population proportion, is computed at 95% confidence, how many samples out of the 100 that you, let's say, compute would not contain P? So think of this, but gigantic. So 100 of these lines, all the way up on the graph with P hypothetically dash lined into the middle here. What they're saying is out of 100 of these lines, if we're at 95% confidence, how many would fail? They wouldn't contain P. Well, we know how many would. We would know that 95 would, out of the 100, would contain P based on 95% confidence. Therefore, how many wouldn't? Well, how many are left? 5 out of 100 would not contain our true proportion P. Once students understand the concept of confidence, at least mathematically speaking in statistics, then the question they often ask is, well, why don't we just use the highest confidence possible all the time? Some might even go as far as going, why don't we just use 100% confidence? Well, let's get that out of the way for a second. So just remember here, we're using samples in order to estimate populations with these intervals. P hat to estimate P. So there's too much sampling error there for us to be 100% confident in the results. And in the reality, in statistics, this is estimation, this inferential stuff that we're doing. So 100% confidence just doesn't exist. So I do agree that it makes sense to, at least initially when you learn this, that we should probably be using like a 95 or 99% interval, or even higher if you can get there, 99.9, whatever it is, in order to estimate a proportion, just because we're more likely to catch P. There's a footnote to this that sort of explains why statisticians would not do that. If you look at an example I have thrown up here, it says, in a poll of 200 people in the US, 11% stated they are currently on a gluten-free diet. So what I did here was I computed a confidence interval that represented the proportion of people in the US that are on a gluten-free diet. I did it under 90% confidence, and I did it under 99% confidence. And I basically generated it myself here using a computer, which you can do, and I ended up with the intervals that you see over on the right. So as a summary, all I did here was raise the confidence. In other words, I created a higher confidence level. So my question is, what did that do to the interval? Did that shorten the interval, or did that lengthen the interval? So in other words, going from here to here, did the interval get shorter or did it get longer? Well, clearly you can see that this value, this interval up top here, starts at 0.07, whereas the one below it starts at 0.05. It's before it. Whereas this one's high end starts at ends at 0.146, whereas this ends higher. So clearly the bottom interval is longer. So clearly when we increase the confidence level, we increase the length of the interval. Note that this fact should make sense logically as well, only because if you look at the formula here, when I computed this interval versus this interval, p hat and n are going to stay the same. N is here and p hat is here. Those aren't going to change, which means the only thing that's going to change when I increase the confidence level is the critical value here, because alpha is going to change. So if you look at the table right here, if I increase the area that's basically in our confidence, that means that our upper tail area is going to decrease, which means we're going to head this way in the table as our confidence level increases. So therefore, look at the z values, our critical values. What are they doing as we go this way? They are increasing. So all I'm doing by going from my 90 to 99% confidence interval is I am increasing this value right here, our critical value, which is going to increase the margin of error, which is going to make the confidence interval longer. Okay, so here's the big punchline. We've clearly increased the length of the interval by increasing the confidence level from going from the top interval to the bottom one. But which one of these is more accurate? Think about that for a second. If we're looking at these two intervals, here's a good way to think about it. Think of P. So we're trying to catch P, right? The true proportion P. Think of P as a needle in a haystack, right? Would we be more confident in finding the needle if we had this circle? Or would we be more confident in finding the needle if we had this circle? I think most people would be like, well, duh. I mean, if we need to find a needle, we'd much rather have a much smaller area to look through, right? Well, look at these intervals. Which one would you rather find P in? Well, you'd rather find it in a shorter interval. So I know this is 3D and this is 2D, but the same logic holds. I'd rather have a small interval to find P, so I would consider that more accurate. So what has happened? By increasing the length of the interval, I have actually decreased the accuracy of the interval. Welcome to the world of being a statistician, right? So we have, your options are to have a higher confidence or a higher accuracy. They actually don't mean the same thing, mathematically and statistically. So what ends up happening is it's almost like a seesaw balancing act, where you're like, well, I'd like to have as high a confidence as I can get so that I can have as high as accuracy as I get, which is why they often end up quasi on the middle at like 95% confidence. But there are times where you might want to have one be better than the other. But that's the reason why we can't go crazy with the confidence level, because we basically decrease the accuracy of the interval. So the question of the day, I guess, would be, is there a way around this? Is there a tool for statisticians to be able to, let's say, maintain a level of confidence, but still increase the accuracy of the interval? Thankfully, there is. What I've done is I've basically taken my interval at the top over here, Roman numeral 1, and I've brought it down to here. You'll notice everything is exactly the same. I've also reminded you that the sample size is at n equals 200, just like here, right? But I've created a Roman numeral 3, a new interval here, that is still maintaining the same level of confidence, 90%, but I have increased the sample size to 500. So basically, what have I done? Larger sample size. Okay, so remember over here, I increased the confidence level, so now I'm increasing the sample size. So what does that do? Well, the first question was asked was, what is the length of the interval compared? Well, from going from here to here, you can clearly see that we have narrowed the interval. We have a larger low value and a smaller high value. So what have we done? We've actually decreased the length of the interval. And based on what you've already learned, when we decrease the length of the interval, remember over here, we basically get a more accurate interval. So we have increased the accuracy of the interval. This is wonderful for statisticians, of course, so they can basically maintain the same confidence, whatever it is, whatever they need or require, and they can still increase the accuracy of the interval. So it's a way around the seesaw effect that we saw in the previous problem. And just to wrap this up, to make sure everybody understands completely here, the concept of accuracy right here, that was more of a general term that we used for like our typical English language. But in reality, in a confidence interval, what makes it more accurate is that it's shorter. And if it's shorter, that means a smaller margin of error. So when statisticians are, creating confidence intervals, what is their focus? They want a higher confidence level and a smaller margin of error. So it's not exactly out of bounds to think that there will be times where statisticians are given requirements for their research. It might say, listen, we need this at this confidence level, let's say 95, 99%, whatever, and we need this margin of error to be this. And what the researcher will have to do is they'll have to go and do a little bit of computation and figure out how many people that they have to sample in order to pull this off. Believe it or not, it turns out that we have the tools to do exactly that. If you look at the formula for our proportion interval, remember that this entire right side is the margin of error. So what I've done is I've come over here and I've copied this and I've left out the point estimate. So the p hat that's normally on the left side, I got rid of that. I got rid of the whole interval. And I've just set up an equation where the margin of error here, right, is equal to our critical value, which comes from our confidence level, times our p hat 1 minus p hat over n. So just to be clear, to reiterate, if we want our margin of error to stay put, then that means this value will actually be a number on the left side of the equation. And if we want our confidence level to stay the way it is, then this critical value will stay the way it is. So if you want to figure out what sample size will ensure that to happen, then it should make sense that we can solve for this variable n and get an equation to do that. All right, let's do some algebra here. We need to get this z alpha 2 out of here, away from the radical, because remember, we're trying to solve for n here. So we're going to divide both sides by z alpha over 2. Okay, I'll do it over here for you. Okay, our z alpha over 2 wipe, and we end up with this is equal to the radical expression p hat 1 minus p hat over n. Next, the radical itself, we need to get rid of that. We need to get this n isolated somehow. So we're going to square both sides. Okay, if we square both sides, we'll take the square to both of these variables. We'll get this. And on this side, we're going to get just what's inside the radical expression. There are a couple ways to do this, but the easiest way right now is that if you look at this very carefully, this whole thing is what we call a proportion from algebra. So like a proportion would be the equivalent of two ratios. So AB equals CD. And what would we do in that scenario if we wanted to solve it? We would cross multiply. So that's what we're going to do next. We're going to cross multiply these guys. We're going to get e squared times n is equal to p hat times 1 minus p hat times z squared alpha over 2. Finally, we have n almost isolated. We just need to divide both sides by e squared. I'm going to do a little rearranging to make it look nice. This p hat 1 minus p hat is going to stay on the outside. And I'm going to take this e squared and I'm going to put it underneath the z squared alpha over 2. That's legal because it's multiplication. And what we end up with is the formula for determining the sample size given a set margin of error and a set confidence level. Just a quick note here, this formula can look like this, but this portion of it over here, you can also bring out the square. So I believe the formula that you see in your formula sheet actually looks like this. Either one would work fine in determining the sample size. They both mean the same thing, but just a note there. The last order of business here is to see how this works in an example, right? It says a researcher would like to estimate the proportion of all children that have diagnosed with autism spectrum disorder, ASD, in their county. What sample size should the researcher use to get a margin of error to be within 2% at 99% confidence? The CDC estimates that 1 in 68, or 0.0147 children, are diagnosed with ASD. The good thing about these problems is that they're really, in pretty much everything we do, we're given the sample size. You'll probably notice that along the way. This is going to be the only scenario in which you're going to be asked for a sample size. So this will be a good hint to use these formulas when you're looking at problems on an exam or on homework. Okay, so looking at this formula again, what are the key things that we need? We need p hat. That's right off the bat, so let's take a peek. So it looks like they have p hat right here in the problem, 0.0147. We need z alpha over 2. So in order to find z alpha over 2, we need the confidence level. So it appears that the confidence level is right here at 99%. Remember, the strategy is we need alpha over 2. We need to find alpha first. That's always 1 minus the decimal equivalent of the confidence level. That'll give us 0.01. Alpha over 2 will therefore give us 0.005. So basically, alpha over 2 in this problem is 0.005. The last thing we need is we need the margin of error. It appears that that is also provided to us in this problem right here. So E is going to be equal to 0.02. So why don't we put p hat up here too, just so that we have it, 0.0147. So what this ends up being is a pretty straightforward calculation. So we're going to put 0.0147 here and here. We go over to this side. The bottom is easy because the margin of error is 0.02. We're just squaring this. The z alpha over 2, we have to go to our table. We have to look up where it's 0.005. So right there. So we go down this column all the way down. We're going to get 2.576 as our key value. If we do all the math for this, we can do it all at once. Just be very careful, again, with parentheses and such. You should end up with a value that's approximately 240 let's say 28 for the value. All right, your instinct here might be to just circle this and move on, but you actually can't because this is not the answer. It is n for the problem, but the mathematics doesn't understand real life and real life scenarios, and it's clearly we can't have a fraction of a person, which means your answer has to be a positive integer for that problem, for these problems. But there's also something else at play. Most students would have the instinct to round based on their common everyday rounding rules, which means you would round down to 240. The problem is the only way that we can capture this margin of error and this confidence is if we reach 240.28. If we don't reach that, then something is not that we need to happen is not being done or not being qualified for that. So the only way that we can absolutely ensure that these are met is if we go up always. So the directions will always be in these problems round up no matter what. It'll be weird, but it is going to be part of your grade. I believe the rounding up mechanism is about 2 points on an exam. So make sure that you round up no matter what. Even if your instinct is to round down, don't do it. So you're going to round up and you're going to get let's do n equals 241 just to be more specific. Take n equals 241 for our sample.